Welcome to The Explainer. Today, we're going to level up from basic linear regression. We'll explore how to build models that aren't just accurate, but are genuinely insightful, capturing all the real-world complexity that makes data so interesting in the first place.
So you've built a linear model, right? Your R-squared looks pretty good, the p-values are significant, but is it really telling you the whole story? Because so often, a basic model just completely misses the crucial complexities and hidden relationships in your data, and that can lead to some incomplete or even totally misleading insights.
Okay, so let's start by moving past that simple, straight-line approach. It's time to give our models the tools they need to handle the nuances and patterns that are truly driving the outcomes we're trying to predict.
I mean, just think about it for a second. Real-world data has synergies, where two things combined are way more powerful than they are by themselves. It has categories, not just plain old numbers. It is packed with hidden relationships that a simple straight-line model just flies right over, completely missing the point.
So how do we actually fix this? Well, let's look at two key extensions that are basically superpowers for your analysis, allowing your model to finally understand these more complex dynamics.
All right, superpower number one is understanding interaction effects. You can really just think of this as teamwork between your variables. It's when one predictor actually enhances or even changes the impact of another. It's not just 1 + 1 = 2, it's more like 1 + 1 = 3. That's synergy.
So what does this look like in practice? Well, if we look at this R code for modeling advertising data, we're not just looking at the individual effects of TV and radio on sales. You see that little TV/radio term? That specifically tells the model, hey, also check for their combined synergistic effect.
And the results? They're fascinating. The model confirms that the interaction is significant. What this means is that radio ads actually make TV ads more effective when they run together. Now, if you're a marketing manager, this isn't just a cool statistic. It's a budget-altering discovery. You don't just spend on TV or radio. You strategically time them together to maximize your return. A simple model would have totally missed that.
But what happens when our data isn't a number, like advertising dollars, but a category? Things like ethnicity, gender, or like we see in the credit data set, whether someone is a student or not. How does a math-based model even handle that?
We use this really clever trick called a dummy variable. We basically create a new column that acts like a simple on-off switch. For student status, for instance, we'd have a column called student, and 1 would mean yes, they're a student, and 0 would mean no. Just like that. We've turned categories into numbers our model can finally understand.
Now here is a super important rule of thumb. For a category that has k different levels, let's say you have a variable for region with north, south, and west, you only create k-1 or 2 dummy variables. Why? Well, because that third category, north in this case, becomes the baseline. The model then measures the effect of south relative to north and west relative to north. Following this one simple rule prevents a statistical trap called perfect collinearity, where your variables become redundant and just confuse the heck out of your model.
All right, so let's move on. With all this new modeling power, well, with great power comes great responsibility. We absolutely need to learn how to spot the hidden dangers that can completely undermine our results and lead to some really faulty conclusions.
The first major danger is something called collinearity. This is what happens when two of your predictors are highly correlated with each other. It's kind of like having two people trying to explain the same thing at the exact same time. It becomes impossible for the model to tell who's actually influential, and your coefficient estimates can become really, really unstable. This thing is a silent model killer. So the big question is, how do we find out if our predictors are secretly redundant and just stepping on each other's toes? Thankfully, we don't have to guess. We have a diagnostic tool called the Variance Inflation Factor, or VIF for short. In simple terms, the VIF tells us how much one of our predictors is being explained by the other predictors in the model. So a high VIF score means a variable is redundant, and its results just can't be trusted. Interpreting the VIF score is pretty straightforward. A score of 1 means no correlation. As you can see on this chart, scores around 1.5 or even 4 are generally fine. But a VIF score greater than 5, and especially over 10, that's a major red flag. That high bar at 12 tells you that predictor is highly redundant and its effect is being dangerously distorted by other variables in the model. And the solution is pretty direct. Once you've detected the problem using VIF, you've got two main options. You can either remove one of the highly correlated variables, or you can get a little creative and combine them into a single, more representative predictor.
Another key danger to watch out for is non-linearity. Remember how we started by saying the world isn't a straight line? Well, if your model assumes a linear relationship, but the data is clearly curved, your predictions will be systematically wrong. The first step to spotting this is to look for obvious U-shaped or funnel-shaped patterns in your model's residual plots. If you see them, you've got a problem.
Okay, let's put it all together. Building a great regression model isn't just about adding fancy terms. It's about balancing that predictive power with careful, responsible diagnostics to make absolutely sure your insights are valid.
So here is your takeaway checklist of common pitfalls to avoid. First, ignoring interactions and missing those key synergistic effects. Second, overlooking collinearity and ending up with unstable, unreliable results. And third, not checking your assumptions with residual plots, which can lead you to draw completely invalid conclusions.
And this really is the bottom line. Using things like interactions and dummy variables gives your linear model incredible flexibility to handle real-world data. But it's the diagnostic checks for things like collinearity that ensure your powerful model is also a reliable one.
So this leaves us with one final big question. We've just learned how to supercharge our linear models to handle a lot more complexity. But what happens when the underlying relationship in your data isn't linear to begin with? What do you do when you need a completely different approach? Well, that's a question for our next explainer.